very interesting things. What I was thinking is, is my whiteboard visible?
Yes, sir.
Yes.
Okay. Yeah. Okay. Thank you. And I would request you to keep your devices in silent mode. And whenever you want to talk with me, then only you talk with me, right? Okay, that's good. So I would start with a very short recollection of what you had been studying in the previous classes. So we had been talking about finite state machines, right? We had been talking about finite state machines in general. And finite state machines have generally two forms. One is the deterministic one, and another one is the non-deterministic one, right? The deterministic one is called a deterministic finite automata. The name comes from the definition only. And the non-deterministic one is called the NFA. And NFA also has two categories. One is where epsilon transitions are allowed, and where epsilon, want to say something? Are not allowed, right? Is my board visible? Okay.
Yes,
So
sir.
this is what we had been studying, right? And for that, we also studied certain theorems that assert the equivalence of these models, right? So in a sense, from all the previous classes, what you have learned is, if there is an epsilon NFA, then it is always possible to create a normal NFA without epsilon transitions. And in turn, it is possible to create a DFA. And all these three are in turn connected to some algebraic forms of the languages. So when we talk about these models, we also associate these models with the job of accepting certain languages. So there is a language that is accepted by epsilon NFA. There is a language that is accepted by normal NFA. There is a language that is accepted by DFA. And in fact, there are theorems T1, T2, and T3 that says that, okay, in fact, all the languages of all these three descriptions of machines are essentially equivalent. So there are theorems that assert the equivalence of these models, right? That is what you have learned. And what you have learned is there are theorems that say that, okay, always from an epsilon NFA, we can convert to a NFA. Now, what does that mean? What does that term conversion means? It says that if there is an epsilon NFA for a particular problem, for acceptance of a particular language, there is always possible to create another NFA without epsilon transitions to accept the same language. So L2 becomes essentially equal to L1. And if you land up in a NFA, there is another theorem T2 that says, okay, I can always convert that particular NFA to a DFA. And in a sense, all possible NFAs to all possible DFAs, right? To generalize, to get rid of the non-deterministic factor and to land up with a more deterministic model. And in a sense, then you say that, okay, L3 equal to L1 equal to L2. And what I mean is very simple. If there is a language accepted by this model, there is always another model without epsilon transitions accepting the same language. And there is always another model that is more deterministic accepting the same language. That is what I mean by writing this. Got a point? Now, to come back to, so today's class will be essentially on defining the algebra. On defining the algebra that says that, okay, all these languages, the language of the epsilon NFA, the language of the NFA, the language of the DFA, since they are essentially same, if I can tell it in a different manner, there can be no language that for which a DFA exists and for which a NFA doesn't exist. Right? There cannot be any language for which an epsilon NFA exists, but NFA doesn't exist. There cannot be any language for which an NFA exists, but for which a DFA doesn't exist. So if there is a language accepted by epsilon NFA, that particular language is always going to be accepted by an equivalent NFA. And that particular language, again, can be accepted by a DFA. It is always possible to create NFAs and DFAs from any given epsilon NFA. Now, with all these three models, today's I will primarily start discussing. That discussion will take 2 classes, I think. I will start discussing about an algebra, right? That says that, okay, all these languages can be algebraically represented. All these languages can be algebraically represented. And if I say all these languages, this will be wrong, because all these languages are essentially equal and they are called regular languages, right? Regular languages. And regular language is the language that a finite state machine accepts, a finite automata accepts, and finite automata includes epsilon NFAs, equivalent to NFAs, equivalent to DFAs, right? Only their representations are different. Now let me come back to change the mood of this class. Let me come back to see, and let us talk about some symbols A, B, and C. Please note that I denote the symbols with small letters, right? And I denote the states with capital letters. This is only just by notation, nothing. And this is the start step. This is the accept step. And you connect through epsilons. Now, if I ask you, can you describe the language accepted by this epsilon NFA? What should your answer be? If I ask you, can you describe the language accepted by this epsilon NFA? Now it is quite obvious from the it is quite obvious from the construction. 1 minute, please. It is quite obvious from the construction that what we intend to do is the states are having the properties that A is responsible for taking care of the small a's, B is responsible for taking care of the small b's, and C is responsible for taking care of the small c's, right? And they are connected with epsilons. So my question is, can you describe the language accepted by this epsilon NFA? Yes, who was talking?
Sir, a string that contains A, B, and C.
Okay, so you say that a string that contains A, B, and C, right? So this is your answer.
Sir.
Is it? Right?
Yes, sir. Yes, sir.
A string that contains A, B, and C. Now this is not a very this answer. I take your answer and build an answer that is perfect, more perfect, based on your concept. A string that contains A, B, and C. I will add strings that contains A, B, and C in a specific order such that there are A's followed by B's followed by C's, right? Now, is it a more perfect answer? Strings, I have added A's here, strings that contains A, B, and C in a specific order such that there are A's followed by B's followed by C's. Why? Because of the inherent recursiveness. You generate more and more strings with only 3 states, right? Okay, so why do I say this? I say this because the diagram was A, state B, state C. There were symbols A, B, C. By notational, by notations, this means that you can recurse on A and accept many A's, right? You can accept many A's. That gives you A star. What does it mean? Either you get an A. If you get an A, you can have many more A's. This circle denotes many A's, right? So rather, I would write A plus to indicate that I have more than one A's. This is B plus, one B and many more B's. I recurse. This is like this. Now this is the final state and there are epsilons. So if I start here, what I can do is I can think of not taking any A's, not taking a single A and slipping to the state B, not taking any B's, not a single one, and slipping to this state C and accept. That means I accept epsilon. Not taking A, not taking a B, not taking a C. Do you agree? I accept an epsilon like this. I start here and I slip to this state because there is an epsilon. I slip away from A to B. And then from B to C, I again slip away. It's a slippery floor, right? And I accept. So I accept epsilon. So epsilon means no A's, no B's, and no C's. This epsilon can be interpreted as no A's, no B's, and no C's. Nothing. It has nothing. It is epsilon. Or you can have a single A. You can have a single A like this. Okay, let me take the red color. You can have a single A like this and then slip to B with epsilon and then slip to C and accept because this is an accepting step. So you can have a single A. Similarly, you start here. You can directly slip to B, take a single B and slip to C. Thus, you can have a B. You can start here. You can slip directly to B. You can slip directly to C and take a single C. Or you can have many A's. You can have 15 A's, for example, right? Followed by, sorry. Yeah. So it will be, if you can have 15 A's, you can have 15 B's, you can have 16 C's. Likewise, you can have a single A followed by a single B. You can have a single A followed by a single C, no B's. You can have a single A followed by two B's and a C. You can have single A, single B, single C. You can have a single A and 100 B's and 500 C's. Can you have? Yes or no?
Yes, sir.
Yes. So that said, the language of this epsilon computation should be A star, B star, C star. What does it mean? any number of A's followed by any number of B's followed by any number of C's, right? And that any means there can be zero occurrences of A's also, any number. You can have zero number of A's like this. You can have, for example, the string single B, it has zero number of A's and zero number of C's. The string single C, it has zero number of A's and zero number of B's. The string C16, it has zero number of A's and zero number of B's, right? Any number of A's followed by any number of B's followed by any number of C's. This is the most generic algebraic expression to express the language designed by this machine. So you have in your hand two things to work with. One is machine-based construction and to think about strings, and you have an algebraic way of thinking about strings. Is it clear? Yes. So let me come back to the definition that I gave, that I preferred over the answer that you gave, right? Strings that contain A's, B's, and C's in a specific order such that there are A's, comma, followed by B's, comma, followed by C's. So A's followed by B's and followed by C's is that particular order that I'm talking about. So you can have any number of A's followed by any number of B's followed by any number of C's, but you cannot have, for example, a string like A, B, C, A. You cannot have this order. If there are A's in your, there are two A's in the string, right? So this is a string that has two A's, one A and second A. So if you have A's needs to be at the very first portion of the string. And once all the A's has been consumed, you can have as many number of B's. You can have any number of B's. But once all the B's are consumed by your machine, you can have C's, right? But you cannot have an A after a C. Or you cannot have a string like this. You cannot have an A after a B. That is what I mean by a specific order. Why? Because your model doesn't allow to go beyond that order. Your model was very simple. There are three states, A, B, and C. Like this, you only had forward arrows, but you didn't have a backward arrow. Did you have a backward arrow like this? Say on epsilon? No. Did you have a backward arrow like this on epsilon? No. Did you have a backward arrow like this on epsilon? Say no. If you had these backward arrows, then you could have any number of A's, then any number of B's, again come back and have some A's, again go here and have some C's. So you could have had something like A, B, A, C. But there are no other arrows like this. We started with the model as simple as this. We only had forward arrows, right? So that is very important, a specific order. So let me come back to the story. So we talked about, just now we talked about A star, B star, and C star. Now that you had applied certain theorems, certain construction-based proofs, and you then converted that particular epsilon NFA to a normal NFA, and that normal NFA looked something like, if I'm not wrong, it looked something like this picture, say. So we started with this picture. There's a start. There is state A, this is state B, this is state C. C was accepting state. You were consuming A's, B's, and C's like this with epsilon, right? So you had been accepting A star, B star, C star. So this expression, this algebraic expression expresses a language, right? So the language expressed by this expression, say this expression BR is be denoted by R. So the language of this expression is the language of this model. And that language is a collection of strings like epsilon, small a, small b, small c, double A, B, double B, double C. I'm ordering, right? Like this. And you applied certain theorem and converted that epsilon NFA to some NFA like this. In order to accept epsilon, you made the start state A an accepting state. And then you thought about where you are going. You are consuming A's, and you are on a single B, you are going somewhere, some state B, where you are consuming more B's, and then on B and C, you are going to some state. A, B, C. Now, is it the correct NFA corresponding to this epsilon NFA? Can you please check? You can use your notebooks. There's no hurry.
So could you repeat the question once? Actually, my net got cut off.
Yeah. Okay. Did I get disconnected for some time?
No. So it was my internet
Okay.
side.
Okay. What I was saying is, this is just a recollection from the previous class. So previous class, madam was taking an example of this epsilon NFA, right? This was the epsilon NFA, and you applied certain construction-based theorems and converted that epsilon NFA to this NFA. So this was the NFA, right? It had no epsilon transitions, and it accepted the same language, LR equal to the same language here. And the regular expression for this language is same, A star, B star, C star. So my question is, can I just verify? So on state A, I am accepting, see, I have made this start state the accepting state. I can always make the start state accepting state. There is no rule forbidding me to do so, right? Do you agree? Remember, in your 5 tuple, Q was a set of states and F was a set of final states, and F can always be a subset of Q. You are allowed to do so. So you made the start state an accepting state, right? So
Yeah.
by virtue of this, you accept epsilon. Now there is an A, so you accept as many number of A's, as many number of A's. Then if you have a B, then if you have a single B, you can slip here, but don't accept. But your single B needs to be accepted in this model. So you have an arc on B here to accept a single B. So you can accept a single B, right? So single B you can accept, single C you can accept. If you have two B's, so go from A to B by this B and go from B to C by this B. So you have two B's. So you can accept a single C like this, I have already mentioned, and you can accept many C's like this. C. You directly go here and accept via this, right? If you have more than two B's, okay, one B, the second B, the third B on this, right? Do you agree? So this was an NFA without epsilon transitions. Agree?
Yes, sir.
Yes.
Okay. Yeah, everybody agrees, I hope, right? My board work is not extremely good. I apologize for that, but I hope things are understandable, right? So what I mean is, now let me come back to notations, because we need to bank on notations to define that algebra, and in turn to define expressions, algebraic expressions called regular expressions, that is capable of expressing the language of an epsilon NFA, and if it does, it should be capable of expressing the language of an NFA, and if it does, it should be capable of denoting the language of a DFA as well, because all these models are equivalent as far as acceptance of languages are concerned. Done? Okay. So if I want to talk about notations, we need to concentrate more on notations. So we had enough discussions on models. So let me write down the yeah. Am I audible? Hello.
Yes,
Hello.
you're audible.
Okay. Okay. So in case of a DFA, remember all finite state machines you had talked about Q, sigma, del, Q0, F. Q was a set of states, F was a set of final states. F can very well be a subset of Q. Sigma was a finite state of symbols. We denote symbols with small letters. Delta was a transition function that helps you to transit between states. So delta can be written as Q cross sigma takes you to Q, so that tuples like you are in a state called Q, you consume a symbol A and you go to another state called P. That is delta, right? Agreed? Now you come to NFA, it again had that same 5 tuple Q0 and F, and here del was something like the non-deterministic factor. It was taking Q cross sigma to 2 to the power Q. That means del, you are in state Q, you consume a symbol A, and other than going to a single state, you go to a set of states, right? This was simple, right? And what is the most general form of set of states? A finite set of states. How many such combinations you can have? You can have a maximum of the power set combination. Done? Agreed? In case of epsilon NFA, you again had Q. Now you had sigma union epsilon as your input alphabet, because you allow transitions on epsilon, right? And then you had D, del, you had Q0, you had F. Agreed? So your del looked like Q cross sigma union epsilon was taking you to 2 to the power Q. Done? Agreed? So the model is still non-deterministic. It is 2 to the power Q. That means you can go to set of states other than going to a single state deterministically. That is, you start at Q and on consuming A, you know that, okay, I'm going to P only. But here in consuming, in case of the NFA, you consumed a symbol, you had been on state Q, and you are not telling deterministically that, okay, I am in P2. No, I can be in P1, I can be in P2, I can be in P3, I can be in many other states, right? And that's why you had Q cross sigma taking to 2 to the power Q, because 2 to the power Q gives you the most exhaustive such set of states. So here you denote, here you, even if your del QA takes you to P1, it may be the case that it takes you to P1 only. You have to write like this in set notation, right? It may take you to P1, P2. It may take you to P2, P3, P4. Anyway, it depends on the size of Q, because it determines the size of the power set. So these are all elements of the power set. So these are all elements of 2 to the power Q. Right? In case of epsilon NFA, what did you do? You had to include epsilon, but epsilon cannot be a member of sigma, because sigma contains physical symbols like A, B, C, D, right? Okay. Epsilon is not a physical symbol. Epsilon is a string, right? It's an empty string. So in order that you can allow transitions in epsilon, in order that you can write some del Q epsilon, in order that you are able to represent del with such that's why you have something like sigma union epsilon. Yes, am I audible?
Yes, sir, I think it was
Hello?
yes,
Yes, sir.
Okay. You cannot hear me?
sir, now I can hear you, sir, but I think you got cut off in the middle, sir.
At what time?
Sir, when you were saying sigma, when you were explaining the sigma union epsilon part, sir.
Okay. Let me. Yeah, please talk like this and tell me. Okay, but because I have no control over the network is disturbing a bit. So I was talking about epsilon NFA and going to notations because those are the things that you need to know. So in case of epsilon NFA, you were allowing transitions on epsilon, right? You were allowing something to happen like this, del Q epsilon. Yes or no? Hello?
Yes, sir.
Yes, sir, yes.
Yeah. So if you want to allow this type of things, previously you didn't allow. Previously you allowed only a state and a symbol, physical symbol. You allowed only a state and a physical symbol, right? So if you want to allow epsilon, you want to include epsilon in the extended alphabet. Why extended? Because epsilon is not a symbol, right? And then you also learned that okay, uh, uh, we can make transitions on strings if and only if intermediate states do occur. So you define something like del hat, an extended transition function that takes you from q cross sigma star to q in case of DFA. So this is a DFA column, right? So you said that I can define del hat to be a function, del hat to be a function that now works on some string x. So mathematically, we can think of some string x as a string w followed by a single symbol a, right? And then you say that, okay,
You are not
Sir,
audible.
you're not audible again, sir.
Sir, you are not audible.
So you're not audible.
am I audible right now?
Yes, sir, you're audible
Yes,
now,
sir.
sir.
Yeah, I'm very
Yes, sir.
sorry. My network is not supporting me today. I don't know why. The last semester I took all classes like this. I'm very sorry. Okay. Okay. So let me come back here. So we also tried Is the board visible? Is the board visible?
Yes, sir.
Yes, sir.
Okay.
Yes.
Yes,
Yeah.
sir.
So we also tried to extend this function to this transition.
So you again not audible.
Try to extend those, right? So if we want to extend, then we need to define del hat something like this: q cross sigma star goes to q in case of DFA. Q cross sigma star takes you to 2 to the power q to 2 to the power q in case of NFA, and in case of epsilon. Remember, the whole last class was on epsilon NFA, so I expect an answer. How should I define del hat? The extended function. What I mean is del hat of you are in some state q, and I give you some string, say x. How do you define? Am I audible?
Yes, sir. Yes, you audible, sir.
Okay. So how do you define del hat in case of epsilon NFA? You had a whole class. So if you are not very confident on these notations, then you will find difficulties in constructing regular expressions. That's why I'm talking about notations today.
So
More
with the
about
epsilon
this.
closure, sir.
Yeah, exactly. So what you do is the basic technique is think of x as a string w followed by a single symbol a, and you can do this everywhere here. In case of our DFA, you say del hat qx or qwa or qwa as del hat of qa qw and del of all that, del of this one comma
Sir,
a,
are
right?
you right? Sir, I'm sorry, I'm interrupting, sir. Sir, but are you writing something on the board, sir? Because nothing
Yeah,
is
you
getting
cannot
up.
see. You cannot
No, sir,
see.
it's not getting
You cannot
updated, sir.
see.
No, sir, it's not getting updated. We are still at del hat q epsilon star, sir. That's all that we can see.
Oh, you are still at where?
Sir, sir, in the DFA column, you've written del hat q epsilon star like transitions to q, right? That's the only line we can see, sir.
No, that's not epsilon star. That is sigma star
Sorry,
here.
sigma star. My bad, sir.
Yeah, yeah. So is it now updated right now? Okay,
No, sir.
let me write something. I don't know why it is getting disturbed so much today. I'm writing del hat. Can you see? Q W A. Can you see?
No, sir.
Is it updated?
No, sir.
Okay. Let me restart. Okay, let me restart. Can you see now? If I write,
Sir, no.
No, sir.
cannot see. Okay.
You just
Okay.
want to stop sharing the screen and then again start, then it will be visible, I guess.
Yeah. Once more, please.
You can stop the screen share and then start it again, then it will be visible.
Okay. That's a good idea. That's a good idea. Let me- হ্যাঁ সুচিমিতা দি, এই বারবার কেটে যাচ্ছে নেটওয়ার্কটা, কেন হচ্ছে না বুঝছি না। ও এখন মিউটেড নেই না, আচ্ছা ঠিক আছে। Just give me a minute. Can you hear me? At least.
Yes, sir. We can hear you, sir.
Okay, okay. Yeah, please give me 1 or 2 minutes.
Okay, sir.
Let me just sign out and yeah. Just give me 2 minutes. Now, am I audible right now?
Yes, sir.
Okay.
Yes.
Now, is the board visible? Is it coming back to life?
Yes, sir.
Okay. Now, can you see?
Yes, sir. It's
Okay,
visible
okay.
now.
Thank you so much. Thank you so much. So I was talking that um, if I say that okay, now I want to devise a mechanism so that I can accept strings, right? Other than working on symbols. So we derived something like del hat, and we wrote something like del hat q comma x, and rewriting x as wa. We wrote del hat in case of a DFA because the upper side of the board is not visible. This portion is for the DFA, right? The middle portion is for the NFA. So del hat q comma wa in case of DFA was recursively defined. Mind you, I'm slowly getting into recursiveness, right? So del hat of qw comma a, and this would go on to the lowest level. There will be many dels like this, dels like this, and ultimately it will go on del hat q comma the first leftmost symbol of your string, right? Leftmost symbol of your string, and comma all the other symbols like a, b, c. It will go on like this. Do you agree? And since in case of, so this is the leftmost symbol of the string. For example, the string is A, B, C, D. So you recurse down from here and you find that, okay, this is defined. Now this is defined. You have the definition of this in case of a deterministic finite automata. So you recurse down here and you say that, okay, since this is a DFA, you can say that del of q comma a single symbol is nothing but del hat of that single symbol, right? Because a single symbol anyways is a string. No problem in that, right? In case of an NFA, do you agree? Yes. In
Yes,
case
sir.
of
Yes.
an NFA, yeah, in case of an NFA, you define some extended transition function like this, del at q comma wa, and also you did the same thing, del of del hat q comma w, and then a, you go on like this, and at the end you have many dels acted upon many symbols like this a, b, and c, and in the core you have something like del hat q comma the leftmost symbol, right? And also here, in case of an NFA, since you don't allow, in case of an NFA, since you don't allow transitions on epsilon, again, del hat of q, comma, any single symbol A is del of q, comma, that single symbol A. And the things get
changes in case of an epsilon NFA. Here, what you do is you need to define you define del with q cross sigma union epsilon, and then you are going to 2 to the power q, right? So with this as your construction basis, you construct del hat to be something like del hat q comma x is a string, and we rewrite x as wa, and we say that okay, our basic principle is same, that is we want to calculate del hat of q comma w, and then take a del of that with an a, right? But in case of an epsilon NFA, since you already allowed a transition on epsilon, you already allowed pairings like del q comma epsilon, you allowed these pairings, right? So instead of writing this, what you are going to write is epsilon closure of what? Whatever you do, epsilon closure of del hat qw. Because del hat qw is going to take you to some set of states P, and you need to take an epsilon closure of that set of states. Why? Because that is a mathematical operator that allows you to even think of other states which you can slip to, right? I started the example with a slipping example. You can slip to, and madam has explained much more on that. So in case of epsilon NFA, what you would write, how can you formally write? Now let me enter into formal notations. So del hat of q comma w, you can write as q comma w, sorry, you can write as epsilon closure of a set of states P, right? Where P is now defined as a set of states P such that for any some intermediate state R in del hat q comma w, P is in del of that R comma A. That is what I mean, right? So whatever you do, the thumb rule is epsilon closure P. So if you remember madam's last class, she was talking about two options of taking epsilon closure, two approaches, and she advocated for the second approach that we studied and that we want that you should study, is to take an epsilon closure of whatever you do in case of epsilon NFAs, because that keeps you safe, and that is how you are not going to miss out any states that may not be directly visible to you because you are looking for physical symbols to transit, but here you are slipping to some other states on epsilon, and then you can find a physical symbol, right? So with these notational conventions, I would end today's class, and I will come back to the next class. Next class is on Tuesday, and I hope network will not dysfunction that day, and we'll carry on with these notational basics to define an algebra specifically on sigma, on the concatenation operation, on the union operation, and the star operation. So it's an algebra, right? Right? It seems familiar from your discrete mathematics classes, like the natural number set with addition operation, with the multiplication operation, right? Rings, you had studied, right? So I will end up today's class with this, and what you can do is, you have the recording, you can just play through the recording, or you can go through the Ullman book. To get your concepts right, and based on these notational conventions, we are going to define that algebra and the output of the algebra. What is the output of the algebra? The output of the algebra is a more expressive language for more expressive expression for regular languages. Done? Any questions? I would end today's class here.
Sir, I have a doubt about that
Yeah.
epsilon NFA model there.
Okay. Yeah. Follow. Where do you have a doubt?
Sir, in that model for the string ABA,
Okay.
so
ABA.
won't it get accepted?
Let me redraw it because my board work is such horrible that I will not find, right? So ABA. Let me redraw. Yeah. ABC, right? Epsilon.
Yes, sir.
Yeah, okay. Then what is your
Sir,
question?
for the string ABA, sir, after the loop on B, won't the control go to the state C, which is the final state,
For
and
the
get
string, what is
accepted?
your string? What is your string?
ABA.
ABA, right? ABA,
Yes.
right? You cannot accept ABA. Why? Because state A is responsible for taking care of all the A's, right? So you take an A here. So let me just use the red color. You take an A once, then slip to B with epsilon. Take a B once, and then you have no route back to A, state A, to take another A. There is no route back to A. So you
But
cannot
sir,
have
after the B, there is an epsilon
there
slip,
is an
right?
epsilon
So
that goes to C. There is an epsilon that goes
yes,
to
sir.
some
But
state
as soon
C
as it
that
goes to C, it
accepts,
will
right?
accept.
Yeah. So it will accept an A and a B. It will accept an A and a B. A once, then slip to B. B once, then slip to C and accept. Even if you don't have any C's. So you don't have any C's, right? You don't have any C's. You have an A, slip here. You have a B, slip here, then accept. This is an accepting state. How can we accept A, B, and A? In order to be able to accept A, B, and A with this particular accepting state and no other accepting state added to this machine, you need to have a route like this that comes back to state A, because state A is responsible for taking care of these A's. So in order to accept ABA, you need to transform this diagram like this: A, B, then A, epsilon, epsilon. ABA would be accepted. So in order to accept ABA, you need to change your machine like this: epsilon, B, B, then epsilon, then C, then small c's, and then another epsilon. Now this machine accepts ABA. Got it? Agreed? How does it
Okay,
accept?
sir.
I repeat once more.
Yes, sir.
Yeah, because these are very basic concepts. You need to you can ask me 100 times. So how can we accept ABA? Once you take a once you take a B, come back another time to A, you take A, slip, and accept. Right?
Yes, sir.
This model you are not allowed because you don't have this, and I rub this. Done? Okay.
Yes, sir.
Any other
Thank you,
questions
sir.
anybody has? Any other questions anybody has?
No, sir.
Okay. So I would end today's class, because I would take up from there. I would end today's class to this beautiful recursive definition of Del hat. Del hat of QWA. In case of normal NFA, I'm not complicating things with epsilon NFA right now before ending the class. So it would be del hat of del hat of del hat of, sorry, this would be del of, sorry. So ultimately it would come like this. Ultimately it would come like this. Del of del hat of Q comma W, del of this thing, comma A, and it would be del of del of del of del of, at the core you have Q comma the leftmost symbol, comma other symbols like this, right? Now this defines that now I made a statement right now. Recursiveness is central to such constructions. And when I would have an opportunity to have you in very fresh minds in some class, maybe some class in the first half, a class of 1.5 hours, I would elaborate this statement and say that recursiveness is central to computability theory, right? But before that, myself and Madam had been discussing on how to go on, and I would, based on this class, I would talk about regular expressions and then talk about conversion to other models, from regular expressions to finite state models, and from finite state models to regular expressions, and that too using recursiveness alone and nothing else. And then we would have a class where I would expose you to different techniques and different aspects of computability theory, starting from recursive functions to Turing machines and to language classes. And then again we'll restart the classes according to the table of contents of textbooks, right? Okay. I hope that ends today's class. May not be it ends well, because we had made multiple discussions. Okay.
Sir, could you just go to the bottom, sir, the last line which you wrote, sir? Recursiveness is central. So what is the CT, sir? Can't really
This
understand
is
that.
computability theory.
So what is the
Computability theory.
okay, computability theory?
Yeah, that is what you were studying, right? What you were studying? Theory of
Yes.
computation, right? Theory of
Yes, sir.
computation, theory of computing, computability theory, all the same things,
Okay.
right? So my statement was, recursiveness is central to such constructions, such notational constructions, and even constructions in machines. I can take examples of machines in next class. And what I said was that I would made another statement and prove that recursiveness is central to computability theory as well, not alone to finite state machines, but to everywhere. Every topic that is included in computability theory, right? Okay. Okay. Thank you.
Thank you, sir.
Oh,
Thank you, sir.
yeah.
Thank you, sir.
Bye.
Thank you, sir.
Thank you, sir.